it is ironic that I was talking to you about the different airplane accidents that they were related to fracture and fatigue in the previous lecture. And yesterday we had this rare, actually, it was the first after 2009 fatality, a rare accident in an airplane of Southwest Airlines where there was a failure somewhere in the engine. So presumably something like a blade from the engine broke, and the containment ring that exists around the engine failed, and there was something from this disaster, this mess, that actually flew away and hit a window in the airplane, and a passenger was actually killed as she was pulled out of the airplane through the window. It's not that she fell out, but the force, the differential in pressure internally and externally actually pinned her on the window, and she tragically failed. So I'm repeating what I said yesterday, in the previous lecture. Please wear your seat belts when you're flying. These accidents are rare. This person would have been alive, or I assume that she would have been alive, but somehow the lack of seat belt was tragic in her case. I'm not sure, actually. I'm not sure if the details are exactly like this, but still, it's very important to wear your seat belts. And on the other hand, what we see is that we had a relatively dramatic accident, and yet the airplane was able to land, and a much more larger disaster was avoided. And the one fatality that occurred was pretty much a low probability event. But anyway, these are important things to keep in mind. So in the previous lecture, we started discussing the idea that there is more to energy absorption in crack formation than simply the surface energy that is associated with a propagating crack. And we started to discuss one of the two important aspects of this problem, which is related to the plastic deformation about the crack tip and around the crack tip. So we said that this is a common mechanism of energy absorption that continuously is active as the crack propagates. And to get a sense about this problem, we actually first started looking at the stresses around the crack tip, and I gave you a bunch of formulas there, but the important aspect to remember is that all the stresses are essentially proportional to the stress intensity factor, and that there is a singularity of the type of 1 over square root of r, that is, r is the distance from the crack tip. So essentially, as the distance between the point that we are considering and the crack tip is actually reduced, then the stresses are going to be very large, to the point that actually yielding will occur. And some simple elementary calculations that we discussed yesterday revealed that we can actually estimate the plastic zone, which depends on the stress intensity factor and the yield stress. And actually, the maximum size of the plastic zone corresponds to the point where the stress intensity factor is actually equal to the fracture toughness. And in the context of this discussion, we brought up a very interesting point, which is the difference in plastic zones between situations of plane stress and plane strain. And we have found that for plane stress, actually the plastic zone is larger than plane strain, and since everything else is equal for these materials, practically speaking, the fracture toughness of the same material is larger when the thickness of the component that we are considering is actually very small. And we said that for characterization, we are going after the minimum value of fracture toughness, which is independent of the geometry, and that's the plane strain fracture toughness. So the next thing that we will discuss is actually how do we measure fracture toughness. And I want to say that this is a different test than others that you have seen. It is strange in the sense that actually for the test to be valid, some conditions need to be satisfied, and these conditions are not known quantitatively a priori of the test. So the conditions involve the result of the test, and essentially that implies an iterative process involving multiple specimens in order to get the right value for the plane strain fracture toughness. So there is an ASTM standard, as with most of the tests, and the number is shown here in the notes. There are many different types of tests, and there are many types of tests because we are, well, first of all, let me tell you that this is the most standard one. It's called the compact test, the compact specimen. It is a square test, essentially has two holes where pins are inserted, and we are loading the specimen in that way. It has a machined start of a crack, but that's not the end of the specimen preparation. The important part of the specimen, actually, it is an actual crack that propagates at the tip of the machined slot there, and this crack has to be sharp. If that crack is not sharp, then we're going to have problems similar to the ones that they are common to for the Sharpie test. And so we want to make sure that we have a crack that is atomistically sharp. And the way we do this actually is that we take the machine specimen and then we do fatigue on it. That is a rather small load that will not make it break, but it will actually create an initial crack at the tip of this notch. And once the size of once that crack is being observed externally, then the specimen is ready to be tested. And because the size of this small crack is actually smaller than the size of the slot, essentially the accuracy of measuring this distance, actually the distance from the load to the tip of the crack, is actually not lost by the details of that atomistically sharp crack that is required to be formed. So that is really the specimen preparation for an actual test. I was saying that there are multiple geometries, and the reason that there are multiple geometries is that occasionally there is no possibility to actually form a test of the geometry of the compact specimen test. Sometimes the only thing that you are going to have is something that is actually of this form, or if you have a tube, then it's actually difficult to machine a square specimen there, and this shape is used. If you have a bar that has a round geometry, you can use this one, and on it goes. There are lots of geometries depending on what is the product that you are interested in testing. And for all of them, there is a machined notch, and then there is a sharp crack at the tip of that notch that is formed by by fatigue testing, by fatiguing the specimen. So now, how is the shape of the specimen taken into account? Well, in the fundamental equation for the fracture, for the stress intensity factor, we had actually this formula. In fact, at some point I mentioned to you about the possibility of differences in different geometry, and we talked about surface versus internal cracks. And we said that for the same geometry, essentially we have a factor here that is added in this formula. And so in general, there is a geometric factor here, which is called the geometry or shape factor, that can be actually estimated. And there are plenty of resources, books, and internet resources that can give you this kind of information, where they will essentially give you the shape factor, which sometimes you will see it as F and sometimes you will see it as Y. It doesn't really matter. Now you are grown up enough to be able to deal with inconsistent notations from one book to the other, or even from one lecture to the other. And so, practically speaking, there are resources that they will tell you exactly what is that factor for different cases. So, for example, for the case of a problem like this, where you have a surface crack and you have a finite width, remember in a lot of the experiments that the analysis that I talked about earlier on, I was considering a crack that is actually much smaller than the dimensions of the specimen. But in practice, the dimensions of the specimen are finite, and this can be taken into account. So, for example, here you see this relatively complicated but not unreal expression where F sub g is essentially the shape factor. G presumably is the ratio of A to B practically, where A is actually the length of the crack, and B is the width of this geometry. So for all these cases, there is a shape factor. If you need it, you find it in the books. In books, it is the job of mechanical engineers and people that they are doing things like finite element analysis to come up with these numbers, and they have done a good job over the years cataloging this. We are just using them. So by knowing the shape factor, essentially, it doesn't really matter what is the shape of the test specimen. As long as we know it, we can do the fracture toughness test and try to get results. So we focus now on the compact specimen, which looks like this, as I mentioned to you before. You have to choose your dimensions, which is really interesting because you have a choice of a small or a large specimen, and that can actually play a big role. With respect to pre-cracking and the generation of an anatomically sharp crack at the tip of the notch, we talked about it. I'm not going to repeat it again. Let's see now how about what happens as we test this kind of specimens. What are the possibilities? So when it comes to testing a fracture toughness specimen, we obtained from the testing machine a plot of the load versus the crosshead displacement. Sometimes instead of load versus crosshead displacement, it's more accurate actually to plot the load versus what's called the crack mouth displacement. Essentially, as your specimen is like this, and this is your notch, this is how you're pulling, and this is your crack that propagates there. Essentially what we have is actually we have a clip gauge that is mounted at the entrance of that notch, and it follows how this notch opens. It is preferred than the crosshead displacement, which is often altered by things like the compliance of the whole system, and it can create some issues. So let me actually delete the thing. So what we have in this graph is actually load versus crack mouth displacement. And what we see is we see three different situations, three different potential curves. There is always an initial elastic part, so there is a straight line in all three cases. The problem is that how exactly should we extract from these curves the maximum load? And of course the problem is not at the initial linear part, but it's more when a peak is reached. And the peak can be reached in three different situations. So in the first case, which I call a type 1 here, it is obviously that there is some kind of plastic deformation. Potential sources of this problem is coming from things like maybe not a proper crack has been propagated through fatigue preloading, or sometimes there is too much plastic deformation at the notch. And in order to define the failure load, we have two options. One possibility is actually get the maximum load, which is at the peak of this curve. But to make things consistent and actually more proper for the calculation of the fracture toughness, the custom is to actually take a slope that has 95% of the slope of the initial elastic part, and the intersection of this curve of this 95% slope with the curve, the force opening curve, we call it P5, I guess, for the 5% difference from the initial slope. And in the case of plastic deformation and substantial nonlinearities in the curve, that is exactly the load that we take as the maximum load of failure. I put subscript Q there because this is something that is under question whether it is really a true result related to the fracture toughness. And I will keep this subscript for the fracture toughness in question as well. So for this first case, we take this 95% slope, the intersection with the curve, and we take that point as the failure point. Another possibility is, I will jump into the third case, where you have a straight line, it loads, there's a peak, and then there is a reduction of the load. In that case, there's no ambiguity. The maximum of that curve is essentially the load that we are interested in. The additional complication can occur if there is an initial reduction of the load, but then the load picks up again, and then there is another maximum that is higher than the first one. And in this case, we have the maximum, we have the 5% difference from the slope, this number here, and then we have the initial value. And the suggestion from ASTM is actually, from the ASTM standards, is actually to take the initial peak as the failure load under the condition that P maximum is not more than 10% higher than PQ, that first maximum. So if it is higher, if P max is, if the second peak is higher, then there is a problem, and actually there must be something like a bias from the specimen, either inadequate pre-cracking, some local defect that gave away excuse me, at the first peak. So essentially you need to repeat the test if the difference between P maximum and the first peak is actually more than 10%. So we have three different cases: substantial plastic deformation, an initial peak followed by a subsequent peak, or just a regular test. And in each case we said, okay, which is the maximum load that we're going to take into account in our calculations. In any event, we take that value of the load and we put it in the formula for fracture toughness, and this is a slightly unusual way of writing the equation, but it doesn't really matter. So you have the load here. I believe T is the thickness, W is the width of the specimen. So if it's like this is the width, and alpha is actually the crack size. You calculate your fracture toughness, but this is really not fracture toughness. It can be, but we need to test for it. So how do we test whether this value is appropriate or not? There are two conditions that need to be satisfied. If these two conditions are satisfied, then we say yes, the value that we calculated is indeed the plane strain fracture toughness of the material. So the first condition is to have plane strain conditions satisfied. Okay, what does that mean? Plane strain means that the specimen thickness must be large. Okay, how large? The recommendation from ASTM is this one here. So you take the value of the fracture toughness in question that you calculated from the test, you put the yield stress of the material, and you multiply by 2.5. This has units of length, and it has units of length, I don't know if you remember, but actually 1/6 pi or 2 pi, depending on whether you have a plane stress or plane strain, times K over sigma y square was the size of the plastic zone. So this expression here has actually length dimensions, and if this is smaller than the specimen's thickness, then fracture toughness, the plane strain conditions are satisfied. So this expression for plane strain which is actually this one here, is about 15 times of the plastic zone at the maximum plastic zone, the plastic zone at failure. So if the thickness is much larger than this value, then ASTM standards say that the plane strain conditions are satisfied. But that's not enough. The next condition that we need to actually test is whether yielding around the crack tip is occurring at a sufficiently small enough scale. And this is satisfied if the same value, which is proportional to the plastic zone, is actually smaller than all in-plane dimensions. I remind you that if the specimen is like this is my height, this is my width, and this is my crack size. And so essentially this guy, that guy, they should all be much larger than this expression here. And if that is true, that means the plastic zone at the crack tip is actually small enough, and that gives full validity together with plane strain to the value of the fracture toughness. These are the equations that I was talking to you about in the previous slide. So why is small-scale yielding needed for valid testing? You can probably see this here in a qualitative argument. So if there is a lot of plastic zone in this range, you can see that this kind of test and this kind of test are really not equivalent. So this one and this one may be equivalent, assuming that the presence of the boundaries actually does not interfere substantially with a stress field around the crack tip. And this is satisfied when this plastic zone is actually much smaller than the dimensions, the in-plane dimensions of the specimen. This one, this one, this one, and that one. Okay? So we want this plastic zone not to interfere with the boundaries of the specimen. And this is satisfied when that formula 2.5 times kq over sigma y square is actually smaller than all these dimensions. Okay, so that's exactly the set of conditions, and if that's the case, if everything is satisfied, then we have a valid measurement for the fracture toughness, and what we calculated is exactly the value of the plane strain fracture toughness of the material. If it's not, well, you need to test again. So, in summary, you need a sharp crack, which we usually do by prefatigue the specimen. You need some conditions for the load, and in particular, we are interested in the case where you may have actually multiple failures indicated by peaks in the load opening displacement. As long as the first peak and the second peak are not, and the main peak are not really different more than 10%, then it's okay. If it's not, there is something wrong. There is an indication of some problem in the specimen. Plane strain has to be satisfied. Small scale yielding has to be satisfied, and this actually puts a constraint on the thickness, and this puts a constraint on the overall dimensions of the specimen. So as I said, if all these are satisfied, we got a number. If not, then we need a larger specimen. Larger either in thickness if plane strain is not satisfied, or small scale yielding, or the overall dimensions of the specimen if small scale yielding is not satisfied. Or a better preparation of the specimen if some of the other conditions are actually violated. So it is a tricky specimen. It's a very tricky test that requires iterations if your initial conditions are not, if your initial measurements are coming from a specimen that does not really have the right size.